So we are talking about the concept of friction here. So the most important thing to know about the concept of friction is that friction, most importantly, is a contact force, right? So it is a contact force very specifically that always acts parallel to the plane of contact. And I'll say plane/point of contact, because that's going to become important later when we do rolling motion to say the concept of point of contact. So there we go. And so what is it that friction does? Well, we could talk about an overall notion that what friction is trying to do is it is attempting to prevent relative motion between surfaces in contact. That's a general idea, but it's going to get a little bit more specific when we start talking about the different types of friction. Now, there are many different types of friction, but this course is going to focus on two of those, and those are sliding friction and static friction. So we're going to talk about sliding friction first, and then we'll talk about static friction. Mostly because this is just reviews, so we're just going to do it in this order. So sliding friction, also called kinetic friction. And the reason why we're going to call this kinetic friction is because we want to have nice subscripts here. And so kinetic friction is scripty F sub K. So if we did both sliding friction and static friction, we'd have two FS's, and it gets really messy. So FK. And as I said before, we want to think about this as sliding, because the word kinetic is linked to the concept of motion. And this is not about moving, whether an object is moving or not. It's about whether it's sliding. And there's a distinction there. So let's talk about what that distinction is. If I put my calculator in the piece of paper here, and I do this, the calculator is moving with respect to the table, but it is not moving with respect to the thing it's in contact with, which is the paper, right? The calculator is not sliding because kind of the paper with respect to the table is the thing that's sliding. And so sliding has to do with the fact of two surfaces in contact moving past one another. And so that definition of sliding is really important. So two surfaces in contact moving past one another. And anytime two surfaces in contact move past one another, we get kinetic friction. So a couple of things about that kinetic friction. The first thing is the direction of that kinetic friction. This always acts opposite the relative velocity of the surface in contact. Not of the object, of the surface in contact. And that's going to become important when we have more complex looking objects later in the course. Remember, right now, technically everything is a point mass, so we can't get too complicated with this. But just so that we get this example, if I have a box, and on top of this box, I put another box, right? So box 1, box 2. If we have box 1 moving to the right across box 2, so there's the velocity of 1, right, such that a little bit of time later, we have box 1 over here because it was moving with respect to box 2, we would say that box 1 was sliding with respect to box 2. And if I were to do a free body diagram then of what is going on, right, I would see that box 1, because it had a velocity to the right with respect to box 2, it would experience a kinetic friction force like that. And so that's the kinetic friction force on object 1 there due to its contact with object 2. But oddly enough, object 2 is feeling a slightly different force there, right? Object 2, if you want to think about it, if we pretend object 1 was at rest, it's almost like object 2 is moving to the left compared to object 1, which is why object 2 would experience a kinetic friction force that looks like this. And so this is the kinetic friction force of 2 due to 1, right? Because its relative motion with respect to 1 was to the left, right? Sort of a weird context in order to think about it there, but that's what's going on. So even though object 2 is at rest with respect to the ground, we could pretend it's moving with respect to object 1, which is why we have this kinetic friction force. The other reasons, Newton's third law requires this, that because there's a force of friction on object 1 due to its contact with 2, there needs to be a force of friction on object 2 due to its contact with object 1. Now, why didn't we ever see this before? Well, the reason is because normally you have just an object moving across the ground. So here's my object. Let's say it's moving across the ground like this. There's the velocity vector. It would experience a kinetic friction that looks like this, right? Now, the reason why we don't see that there's another kinetic friction force there is because the other kinetic friction force would be acting on the ground. And generally, we don't care about the ground, so we never draw a free body diagram for it. But that force is indeed there, right? So that's what we've got going on with the direction of the kinetic friction force. And you also note that I'm drawing the kinetic friction force at the surface where it matters. Now, I know we said that these are point masses, so it really doesn't matter, but this is a good practice to get involved in, especially, in more complex problems where you might have, for example, in this problem here, or in the problem with my calculator in the desk, we had a static friction force between here and here, but a kinetic friction force between the paper and the desk, right? So you can have this one object at two different surfaces experiencing two different friction forces, and we want to be able to parse that out. Okay, so that's the direction of the kinetic friction force. Let's talk about the magnitude of the kinetic friction force. And this should be a reminder from last year that the equation for the kinetic friction force is the coefficient of kinetic friction, mu sub k, times the normal force. And that's why we've been finding the normal force and why we care about it. Let's talk about the role of what each of these are in this equation. So first off, the normal force. Now, I want to just make this very clear from the start. The normal force is not the same thing as the weight. The weight of an object does not affect the kinetic friction force as a matter of course. There's a correlation between heavier objects and kinetic friction, but it is not a causation, right? What affects it is Fn. Fn is a force of contact between the two objects, right? This is a force that measures how much the objects in contact press together. So in that light, that's really what normal force is about, is it measures the quality of contact between the surfaces in contact. And so that's why we care about it. So oftentimes, for example, the weight of an object affects how much, like say for example, this calculator is pressing up against the paper. But if I have my hands and I press them together more, it's harder to get my hands to slide past one another. I didn't increase the weight of my hands, I increased the normal force in between them, and therefore increased the friction between them, right? So it's about how much of the surface in contact pressed together. So although weight often affects this, we would have to do a sum of forces equation in whatever dimension Fn is in order to find out what its value is. And the mu sub k is the coefficient of kinetic friction, and this is a measure of the textures of surfaces in contact, right? So it is a pure number, and there's tables of them. So either you have to be given this, or it is the thing to find, right? But like between wood and wood, there's a certain mu sub k. Between wood and ice, there's a different mu sub k. And it's about the surfaces, plural, in contact. It is nonsensical to say what is the coefficient of kinetic friction of this calculator, because the coefficient of kinetic friction of the calculator on the paper is different between the calculator and whatever this substance this desk is made out of, right? So it requires the combination of surfaces in order to do that. Now, mu sub k is always determined experimentally. There's not like some magical formula that you can use in order to find mu sub k given the properties of an object. You have to actually test it out with forces in order to find out what mu sub k is. So there you go. So that's really all we need to know about the concept of kinetic friction, okay? So kinetic friction often slows things down, but doesn't always slow things down. We're going to do the free body diagram and kind of see what happens. All right, let's talk about the concept of static friction, which is the one that gives people a little bit more problems because it's a little bit more interesting, right? So F sub S, static friction. Now, static friction is going to act in a manner to attempt to prevent relative motion between two surfaces in contact when some effect attempts to move the two surfaces relative to each other. So why all that? Well, for example, my object calculator is at rest with respect to what it's in contact with right now, but there's no static friction force, right? Because there's nothing that's attempting to move this relative to that. But if I exert a force on this calculator, say like 2 newtons in that direction, and it doesn't move, I know that the net force on this thing is 0. I can observe that the acceleration is 0, and therefore I can see that there must be some force acting in this direction to cancel out my applied force, and that would be the static frictional force. Okay? But just sitting here, there is no static friction force because there's nothing attempting to accelerate it. Now, the reason why I say effect, not forces, if I exert a force on the paper and accelerate the paper right now, notice I'm not exerting a force directly on the calculator, but if there were no static friction, the calculator would move relative to the paper. So the fact that the frame of reference that the calculator is in is accelerating is an effect that causes there to be static friction on the calculator. Otherwise, the calculator would have moved relative to the piece of paper. So it gets a little bit more complicated that way. So let's talk about it. First, what direction does the static friction force act? It always acts oppositely what the direction of relative motion would be if there were no friction. Okay? So what does that mean? Well, if I were to push this in this direction, if there were no friction, it would accelerate in that direction. Therefore, the velocity vector would have been this direction. Therefore, the static friction is that direction. If I move the piece of paper and there were no friction, the piece of paper would move forwards, but the calculator would move backwards with respect to the piece of paper, and therefore static friction would act forwards on the calculator. Okay? So that's what that is. So if you wonder what the direction of static friction is, you have to say, well, what would happen in this situation if there were no static friction? And then put your static friction force on your free body diagram based on that logic system. Now, what about the size of static friction? Here's the weird thing about the size of static friction. The static friction force has no set value, okay? There is no equation to calculate the static friction force. What do I mean by that? Well, if I push with 1 Newton here on this calculator and it doesn't move, the static friction force is 1 Newton. If I push with 2 Newtons and it still doesn't move, the force is now, static friction force is now 2 Newtons. I push with 3 Newtons and it doesn't move, the force is now 3 Newtons. The only way I know that is by observing the system, doing a sum of forces equation, and finding out the value for Fs, right? There is no set value. Now, what we know exists, though, is I can push hard enough to cause there to be relative motion between this and this, and static friction goes away, and then I'm in the realm of kinetic friction. So there exists a maximum possible value to static friction, but there is no equation for the actual value of static friction itself. Okay? So that is super, super, super important. So because of this, when we put it on a free body diagram, we always put in Fs. And I'll explain what I mean by that. Because what we have an equation for is what does exist is a maximum possible value of Fs between two surfaces in contact. Right? So there's some limiting value, some maximum amount that I can force this object to move before it starts to move, or if you want to think about it as a minimum force until it needs to start to move, right? So hopefully, if you're thinking about there's this convergence of some function upon some value, right, you're hopefully thinking about the concept of limits, and that's going to be super important. We're going to call this maximum possible value of static friction between two surfaces in contact Fs max. So what I have an equation for is Fs max between two surfaces, not for Fs. So when I said we always put Fs on our free body diagram, we're always going to put the actual force of static friction. We're never going to assume it's the maximum value. We would never have Fs max on our free body diagram. I'll show you how this functions in practical terms in just a moment. But what affects Fs max? Well, hopefully you remember from last year, Fs max is equal to mu sub s Fn. So it's a very similar formula to the kinetic friction. The difference here is that we have a different coefficient. And the value for mu sub s between any two surfaces in contact is always greater than the value of the coefficient of kinetic friction. This also is experimentally determined. So meaning between this surface and paper, it might have a mu sub k of 0.4, but its mu sub s is going to be greater than 0.4. And there's no mathematical relationship between the mu sub s for a surface and the mu sub k for a surface. These are experimentally determined, but we have figured out that all mu sub s's are bigger than mu sub k's for any two surfaces in contact. And there are tables and tables and tables that prove this. The reason for that is the physical phenomena then is that Fs max between any two surfaces therefore has to be greater than Fk between two surfaces. We wouldn't say the static friction is always bigger than the kinetic friction. That's false. But the maximum possible value of static friction between surfaces is always bigger than the kinetic friction. That's why it's harder to get it to go than to keep it going. That's what that comes down to. So what does this look like practically? So if I have a box here, and I've got a normal force, and I've got a weight, and I'm trying to accelerate this thing like this, I know, absent static friction, that this thing would accelerate to the right. There'd be relative motion between the surface and the floor, and I would say Fs. And so if the question was something like, what is the value of Fa that gets this thing to move, the way I would tackle this is I would go, well, sum of forces in the x direction is equal to max, and I would say, well, positive Fa minus Fs is equal to max. Now, I know that this system is not accelerating because based on the context, so I know that that's going to go to 0. But what I want to do here is I wouldn't want to plug in this in terms of here because this is just Fs, right? If the applied force is 10 newtons, the static friction force is 10 newtons. The applied force is 15 newtons, the static friction force is 15 newtons, but there's some maximum value here. So the way that we turn Fs's into Fs maxes in an equation is, of course, to take a limit. So we're going to take a limit as Fs approaches Fs max. Another way, the limit I could have taken here is I could have done the limit as Fa approaches Fa max because when you get to Fa max, you're at Fs max. That's the whole thing. So when I take this limit, Fa turns into Fa max, Fs turns into Fs max is equal to 0, and now I can plug in mu sub Fn for that and solve out the way I want to, okay? So that's what's going on there. So let's look at another example of that. If I've got a block on an inclined plane there, and I've got a force of gravity. I will put in a axis, positive y, positive x. We know there's a normal force there, okay? Fg y, Fg x, whatever this angle is this angle, okay? There we go. And I say, well, okay, if I put that there, what is the direction of static friction? Well, that static friction should act up the hill unless Fgx is bigger than Fs, in which case it would start to accelerate down the hill and this Fs would become Fk. So if you're not sure in a situation whether or not it's static friction that's acting or it's kinetic friction, we're just going to put in a generic Fk, or excuse me, sorry, a generic scripty f there. And then we would test, right, is fgx, in this case, greater than fs max? If it is, then that f becomes fk. If it's not, then that f becomes fs, right? So let's make this more interesting then. Rather than that situation, let's put it back on the hill and say I've got an applied force here. And I'm just going to shortcut this a little bit, not look at values. Fg, Fgy, Fgx, right? And say there's an applied force acting up the hill. And then the question is, what direction does static friction act? Because let's say we know it's going to remain at rest, right? Like that's stipulated by the problem. This is sort of an interesting question here because in the last problem, clearly Fs was going to act up the hill, right? But here with this Fa, if Fgx is bigger than Fa, this object, if it was at rest, is going to want to accelerate down the hill, which would mean that Fs would act up the hill, right? But if Fa is really big compared to Fgx, then it would accelerate up the hill, which means that Fs would act down the hill, right? So I would have two different free body diagrams that I would need to do for this problem based on the relative size of Fa compared to Fg, right? So there would be one and only one Fa such that Fs would equal 0, and that would be the one where Fa is equal to Fgx. But if Fa is larger than Fgx, static friction would act down the hill, and if Fa is smaller than Fgx, it would act up the hill. And so I would need to do this problem twice, once to test where Fa is at its maximum possible value that it could be before it starts accelerating up the hill, and one to test where its minimum value would be before it would start accelerating down the hill. So sort of an interesting problem there. And that might be a little bit of a hint to one of the homework problems that you have. So that's what I've got, the difference between static and kinetic friction. If you'd like more, please go to the textbook and chapter 5 and feel free to read those sections. But I just want to leave you with a couple of last things. One, kinetic friction is really sliding friction, right? Kinetic friction's value between two surfaces in contact is always determined by mu k Fn. There's no such thing as like a maximum kinetic friction or whatnot. Nope, it's just what's mu, what's Fn, that's what your kinetic friction is. But static friction is a little bit more interesting. Its value is affected by the size of the applied forces that are acting on it along the direction along the plane of motion, and it kind of reacts to the effects that are trying to get it to accelerate, which is why we always think in terms of Fs. And then if we need to deal with maxes and mins, we would be doing limits in order to do that, and we'll see some experience with that problem when we do the homework on Wednesday.